In this notebook, we will use scikit-learn in action to perform a decision tree-based classification of weather data. This weather data was curated from sensor data of a weather station located here in San Diego, California. And the weather station has sensors that capture weather-related measurements such as air temperature, air pressure, and relative humidity. The data was collected from a period of 3 years, so it has longitudinal information from September 2011 to September 2014. And this ensures also that sufficient data for different seasons and weather conditions are captured. Let us now import our necessary libraries. So we go to our notebook. Hope you located the notebook called Weather Data Classification using decision trees in the zip file for the week that was provided. So we are in week 7, weather classification using decision trees. So I'm going to my first cell, starting to import the necessary libraries to get started with the analysis. The task of classification, as you just learned, is a supervised learning task where we supervise the algorithm to learn how to label a given sample by training it. Here, we will leverage existing methods in the scikit library. As you see from what we import, we will be using the decision tree classifier for this example. So we have import pandas as a PD, sklearn metrics, accuracy score, sklearn, which is the scikit-learn, model selection, train test split, and then sklearn.tree, we import decision tree classifier. So these are all our imports for this notebook. And as a side note, you can import these libraries at any point in your notebook. For instance, when you use them and you're about to use them. But it's also a good practice to have them all listed on top of the notebook, so you will often see them like this in practice. This ensures that the users of your notebook understand what you'll be using when they open the notebook. But it really doesn't matter in practice. So let's ingest the CSV file. Again, the CSV file is also given to you for this week in the folder called weather, and the name of the file is daily_weather.csv. daily_weather.csv. You already learned this. We'll be importing this into a pandas data frame. We'll call that data using the read CSV function. So let's import our data. We'll quickly look at the pandas data frame and the null values in it to give us an idea about the data set. But before that, let's remember this data is collected again from a weather station, right? Let's look at the columns in it. We'll see that air pressure AM, air temperature at 9 AM, and things like that are in the data set, all the columns. And if you look at the markdown cell right below that, we describe what each of these columns are. Why are they named like that? For example, air pressure at 9 AM is air pressure averaged over a period from 8:55 to 9:04 AM, and the unit is in Fahrenheit. You can understand, if you read through this markdown, you feel free to stop the video. You can understand more about this data set before we go on. And of course, we could look at this data frame after, hopefully, you've just read through that. What is this data bits in the markdown? And we see the values for different columns in the data set. And now we can look at the null values in it, if there are any null values. We see that there are some NaNs in this data set. So we see some rows with null values. So let's clean this data frame a little bit to get ready for analysis. This data set was curated a little bit, so there's not much to clean. In fact, very little to clean. But that number column, for example, is just a unique number ID for each entry. We won't need that, so I'll go ahead and get rid of that column. So let's go back to our notebook and delete that number column. And we've just looked at it, right? There are some null values. We'll drop those null values. And remember, the drop NA function in pandas will give you an opportunity to drop all missing values. So let's go to that cell. I'm just storing the number of rows before dropping the null values to a variable called drop before rows. It's 1095 rows. And let's drop the null values using data.dropNA, and we store that slice of the data frame into data again itself as a slice. And then after rows, let's get the shape of that. We have 1064 rows after cleaning those null values. Let's see how many rows we dropped. If you actually execute this, we'll see that 31 rows overall was dropped. Let's call this that we cleaned our data set, and we can now get started with our classification task, which is the main goal as a learning objective from this notebook. We will use a classifier to predict humidity on a given afternoon by looking at the weather in the morning. So it gives us the ability to predict weather in the afternoon just by looking at the morning weather. It's useful in some contexts. And remember, we use the dropNA function to generate a slice of the data and assign it to the data frame instead. Now we'll copy the slice into a new data frame that is not a slice. It's a real data frame, or what we would call, the data was what we would call a view over the original data set. The one that we assigned it, we'll call this clean data, will be a real data frame again. And after this step, we will add clean data a new column called high humidity label. This new column will store 1 for humidity values higher than, as you see here, 24.99. And if we look at the relative humidity at 3 p.m., if it's higher than 24.99, it's going to give us a true-false value. We multiply this true-false value generated by that comparison greater than operator. We'll multiply that by 1, the true-false value by 1, to turn the column into integer values, 0 or 1. And when we actually print that column, we see that we have 1s and 0s. So to summarize what we did here, we created a new variable that's 0 or 1. That's our target variable. And we call this target variable the high humidity label. So we labeled our target variable as high humidity. So if it's 1, we know that value is high humidity or above 24.99. And if it's 0, we know it's below that. Going with the parametric function analogy, y equals fx, we will now create a new data frame called y for what we are trying to predict. So by looking at x, we'll try to predict y. That's the analogy. And we will do this by storing our high humidity label column into y. So now we are storing the high humidity label in our clean data into y. Let's uncomment y here to see what's stored in it. It shouldn't be a surprise that it stores that high humidity labels from the clean data. So now we have our labels stored in y. I'm just going to, for cleanness sake, uncomment y and move on. So we can also print out the first 5 rows of y and clean data to compare the humidity values with the high humidity labels and verify them. So let's do clean data, humidity at 3 p.m. .head. We see the humidity values ranging from 12 to 76 in these 5 rows. and then y.head. And when we look at these, it indeed values, remember, about 24.99, 36, and 76 are ones. They're converted to 1 as a label, high humidity label. And values below that are turned into 0. Now we'll select the features for the data in the morning. Remember that we are using the morning data to come up with a predictor for the afternoon. And we will load all these morning 9 a.m. variables or features into a list called morning features. So here, let's run this one. Morning features, air pressure at 9 a.m., air temperature at 9 a.m. All of this is stored in a list called morning features. After we run this, we will create a matrix or a data frame, in this case, with only these morning features as columns. We will literally copy the values in those morning-related columns into a data frame called X. Remember, again, we are trying to do y equals fx. So that's why we call the labels y, and the input we'll be using to train x. So given the x, we'll try to come up with the y values. That's what we are trying to do. Here, the values in clean data, or now in X, are pretty standard data types. However, if they were lists or other more complex data types, we might have had to use a deep copy. In that case, we would have said inside those parentheses in the copy, deep equals true for the copy function. That will ensure if you have any complicated data types like arrays or lists in your input matrix, they'll be copied over to X in this situation. Now let's double check the columns for X and Y. So we can say x.columns. We see that everything we selected for, within those morning features are columns of X. And Y will have a label, high humidity label, as the column index. Great. So far, so good, I hope. Now we will start building a model. Our first model, a classification model using decision trees. To do that, we will split the data set into tests and training samples. So just as a reminder, we'll need to use, and if you look at this figure here from our slides before, we'll need to use some part of our data for training, and that's the training data, and we'll use the rest for testing. To do this, to be able to do this, we use train test split function to generate these two data sets. Now these two data sets will be slices of our original data set stored in X and labels stored in Y. Let's discuss a little bit the arguments here. Right? We have the train test split. We give it the X, our input, and Y, the labels for training. So in addition to these two, we provide a value for how much of the data we want to test with, called the test size. So we are telling this function, store 33% of the data, keep it, don't show it to the trainer, because we'll use it for testing later. We also have the random state seed here set as 324 in this notebook. Although this seed is changeable, it will lead to different partitioning of the original data set and later leading to different prediction accuracy. So I strongly recommend that you keep it as it is if you'd like to follow along, and you can later on maybe test with different seeds. Okay, let's look at what this function has as a summary. Train test split here takes two data frames and returns 4 data frames, right? It's the X train, X test, Y train, and Y test. Now, please feel free to stop the video. I actually recommend that you do. and uncomment or add to the lines in the next code cell to explore these data frames before we go further. Hopefully you were able to uncomment and run those lines in the code block. Now let's use a decision tree classifier to train on the training data set, and I will name this training data set our decision tree. In a sense, it's a humidity classifier. Here we are trying to fit on the training data set now. We have the humidity classifier, and to the decision tree classifier, we will set max leaf nodes as 10. So this is our stuffing criteria for the tree induction. If we left it as default, it would have been unlimited, making it potentially overfit the tree to the training data. We don't want that. But in general, you need to experiment with it a little bit. And the random state argument in this algorithm is used for splitting the nodes. 0 here is one of the internal states used to build the decision tree. Although, just like random seed before, this one is changeable. Keep it as 0 if you would like to replicate the results in this video locally on your end. Okay? So we use the decision tree classifier. We give it the max leaf nodes and random state. And we assign that to humidity classifier. Next, so we created a decision tree classifier object called humidity classifier, right? We will use the fit method of this object, okay, to make the classifier tune itself to learn from the samples. So we have the humidity classifier.fit, and we give it the training sets for x and y that we split in the code cell before. At the end of this function, we will have a decision tree-based classifier, a model. If we run this, we see that the type for the humidity classifier object is indeed the decision tree classifier. Now, we will use the test data for this prediction to test the model we just built. We will use the predict function of the decision tree classifier object, which was our humidity classifier. This function will accept our test data. So we are doing humidity classifier.predict. It will take x_test, our test data, and that means we are asking the classifier to predict on the test set, which has not seen at all during the training test, during the training phase. Let's run this and display the first 10 values in those predictions. And let's also see what y-test is, because that's the one that we kept as labels from the original data. So we have our predictions, and that's the predicted humidity labels based on what the model learned. And when we gave it the test data, x_test, it came up with. Now, before we move on to look at the errors, let's summarize what we've done. We had an x, which is our input data, and y, which is our label. We created training sets for the input and the labels. We also created a training set. We also created a test set using our input and labels. What we've done is we created a model using the training x and training y's. And we used our test x to create a predicted y. And what we just displayed in predictions is the predicted y's. But remember, in our y-test, we have the labels the actual labels for those data, for the test data. So now we can compare the predictions with the y-test. And when we look at that, the first two values are 0. Then we have 4 ones in the prediction, 5 ones in a row in our actual data. So there's an error there, right? One of them wasn't predicted right. And we have 0, 1, 1, and here we have 0, 0, 1. So again, another value. So we have about 10 values here, and 2 of them were wrong. So overall, this is called an error. For the classification task, an error occurs just like this when the model's prediction of the class label is different from the true class label. We can measure these errors by calculating the number of correct labels, just like I've done now. We had 2 wrong, so if we had 10 rows, it would be that many wrong in it, and we can turn that into an error measure. For example, like we did, if we just looked at the first 10 rows for the generated labels, we can see that the values in the prediction are pretty close to the values in y-tests. But, we can't always count, right? How close? Especially when we have a large number of rows. How do we test the accuracy of our classifier? By calculating the accuracy score. We actually have a function for that. It's called the accuracy score, and if we look at that, the accuracy of our algorithm here is about 81%. We can also define the different types of error in the classification depending of the predicted and true labels. But here we will stop and call this 81% our accuracy score. Okay, let's think. Is this a good enough classifier considering it's only looking at the 9 a.m. measurements to predict the 3 p.m. weather? I would say so, especially for San Diego where the weather varies all the time.